Greetings, welcome to another fun video from iCampSA. So today we are doing another 2024 May-June question paper focusing on momentum and impulse. Yes. Okay, so let's read two trolleys A and B of mass. Okay, let's do this. We're gonna mark as we go. So this is gonna be 3.2 and 2.6 respectively. That means following each other, are held at rest. At rest, very important. That means they're not moving, velocity 0 on a straight horizontal frictionless track. Frictionless track, this already tells us that there is no friction here. Then with a compressed spring between them, and as shown in the diagram below, right? This is before the spring is released. It's still compressed. Then after the trolleys are released, the spring extends to its natural length and falls onto the track, right? Trolley A now moves with a constant velocity, right, to the left, and while Trolley B moves with an unknown velocity to the right, right? This is after a collision. Then Trolley B reaches the end of the track after 1.3 seconds. Okay, then the question asks us to state the principle of conservation of linear momentum in weights, right? Why in weights? Because the formula for it says Pi equals to Pf. The sum of Pi, or the sum of initial momentum, is equals to the sum of final momentum, right? So what is the conservation? So what is this telling us is that the total linear momentum in an isolated system remains constant, right? That's what you can say. Let's write it down so you can see it. So important keywords is total linear momentum, isolated system, constant. Those are the keywords. They need to be there, right? So, okay. Now let's calculate the distance traveled by Trolley B in 1.3 seconds. Trolley B, this is Trolley B. So now we need to be able to calculate what is happening here. But first of all, we don't know the velocity that Trolley B is moving at, right? We need to calculate that velocity first, and then we can move, okay? So we're gonna use this principle that they've asked us before. Because most of the time is they're gonna ask you a question above to state something, and most of the time you're gonna be using that as you go down, right? You're gonna use it somewhere. So let's start with our calculations. So I'm gonna say here 4.2, we're gonna use momentum, this one here, this principle, right? This is F. Then what we're saying here, remember, for before collision, this is before collision. Initially, not collision, before the spring extended, right? Before the spring was released. Okay, so that means here, this is one thing. Let's take it as one thing, okay? Because it's not moving. So here we're gonna say this is gonna be mass 1 plus mass 2. Let's use B, mass A plus mass B. They have the same velocity because they are one system. They are attached to each other. And then we have MVA plus MVB. This is final, right? This was initial. So initially it was 0. So that means here we're going to have, let me just write it down, plus MP all times 0, right? Then that means it's going to be 0 on this side. Then on the other side, let's check. Trolley A moves at 0.4, right, to the left. So we should note that. Remember, momentum has direction also. So that means here we're going to use A, 3.2, then our velocity gonna be minus 0.4. Why? because it's going to the left. So we're going to choose to the left as negative, right? Remember, momentum is a vector, it has direction, magnitude and direction, right? And then this is B. MP is 2.6 VB, because VP, we don't know VP, right? So this is going to be 0, being equals to, let's punch our calculator. Our calculator says it's 1.28 minus 1.28 plus 2.6 VB. We transpose to the other side, we're going to have 1.28 being equals to 2.6 VB, like so, right? Divide by 2.6, 2.6. This goes away, then VB becomes, let's punch in our calculator again and see what we get. Then we get 0.49 meters per second. Now this is of B. Remember, B is going to the right. Okay? Yes, there we go. Now that we've got the velocity, then we can calculate what are they looking for? The distance, right? So how do we then calculate the distance that is covered? Okay, we can use multiple equations, but for now let's choose just one. So remember, V is equals to the change in distance or displacement, and then over the change in time. Okay, we've already got this 0.49. We are looking for distance, so we can just use this, and the time is 1.3 seconds, right? Then we can just cross multiply, and then we get our distance here. So that means this is going to be what? This is going to be 0.6637 meters, or 0.464 meters. Okay, we have gotten our direction, right? So that's how nice it is. So then we move to another question. Now this question is saying the average force exerted by the extended spring on each trolley while they are in contact with the spring is 4.2 newtons. Calculate the time it took the spring to extend to its natural length. Okay, so now let's do this. Let's use impulse 4.3. We know that this formula here, remember this formula here, right? Times over t, like so, right? You remember it. Okay, but in this case we are looking for time. So now let's calculate. Okay, so in this calculation we're going to use one of these blocks. Any of them we should be led to the same answer. Okay, because this force is exerted on both of them, right? So let's just pick one. So if, let's say, we pick block A, for instance, then we're going to have this force here, which is 4.2, right, being equals to the change in momentum for just A. So block A, we have, okay, let's start with change in momentum so that you can see it. So net like this, and then change in momentum with mvf minus mvi, okay, so that you don't get confused. Okay, then we have this 4.2, which is our force. Then we have our mass is 3.2. Vf is, what is Vf? We have this 0.4, right? So now, depending on what we choose our direction to be, let's say to the left, we choose it as negative. If we choose to the left as negative, then that means this force is going to be negative here, and then this velocity, final velocity, is going to be 0 minus 0.4, right? Then minus, this is going to be 3.2, remember it was at rest initially. Okay, so that means it's gonna be 0 this side. Then all over this time that we don't have here. This is the time that we are looking for. Okay, so we end up with something like this. This is what we end up with. Okay, 2.8. Then you divide both sides. So if you made a mistake somewhere, you will know by seeing your time is negative. Time can never be negative. Okay, 0.2. Then we have 0.30 seconds. Okay, we've got our time that we are looking for. Then let's move to the final question here and see what they are looking from us. So trolley B is now replaced by trolley C, which is larger, or which has a larger mass. The same compressed spring is placed between trolleys A and C. The trolleys are then released. The average force exerted by the spring on the trolleys remain at 4.2 for the same period of time calculated, which means it's going to be 4.2 for this 0.3 seconds that we just calculated. So now they're asking us, how does the magnitude of velocity of trolley C compare to the magnitude of velocity of trolley B after the spring has fallen on the track, right? So we're looking for greater than, less than, or equals to, and then we need to explain this answer, right? Then how do we come into this conclusion from the start? Let's understand that first. Okay, let's explain it like this. So you have F net being equals to the change in momentum over the change in time. These two, the time and the F net, are constant in this case. Okay, so that means we're going to say F net times T, then we're going to have P, right? So as we can remember here, we can go back and say, remember, this is M, then this is the change in V. This is what changes. We're just taking one block. Okay, this is F net, also change in time. So in this case here, only the mass has changed. So we changed only M. Okay, so since we changed only M, then we can say, let's do it like so. That means let's divide by V, this side, divide by change in V, right? So we'd end up with something like so. That means you have M and then this. Okay, let me interchange so you can see. F net change in time over change in V, right? So here, this is going to allow us to explain what is happening here. So this is F net times time, change in time, right? This is constant. It's not changing. There's only going to be a change to the velocity or the mass. Okay, so now by looking at this formula, we can say M is inversely proportional to V. What does this mean? That means if you increase M, if you increase the mass, or if you increase this velocity, you should have vice versa, right? If you increase the mass, you should also have vice versa. Okay, so if we increase the velocity here, we should have less mass. But if you have bigger mass, then the velocity is going to decrease, right? That's what inversely proportional means. So if this mass is large, then we're going to have a smaller velocity. So then we can conclude here and say the answer is actually going to be lesser than, right? Less than, actually, less than. Why is it less than? Because, let's state the reason here using another color. We can say mass is inversely proportional. to the velocity. okay, to the velocity or the change in velocity. So if we increase the mass, that means our velocity is going to decrease, right? That's what is happening. But if we decrease the mass, then our velocity is going to increase. Okay, so this is the reasoning. So you just use this and try to be able to explain it in a formula format and also in weights, because now we've got this F net is equal to the change in momentum over the change in time. If we rearrange it, because we are only changing m and we are not seeing m in this change in momentum, you have to rearrange this, because we know that momentum itself is equals to, this is momentum, mv. So that means if we substitute here, then we can see m. Then once we can see m, we rearrange the formula, then we can get our answer there, right? So this is momentum simplified. Okay, so this is the end of our session today. Until then, we meet next time.